So next we're going to discuss causal structures or causal structure. Now, the space-time that we're discussing, which admits Einstein's principle of relativity, it's different from what we call Euclidean space, because if you remember, if we have Euclidean space and we have the distance between 2 points, then if I do a rotation of my space-time, say, I rotate the axes to be so these are the new, say, axes. Then in this new reference frame, this distance remains invariant. Whereas the space-time that we are looking at, it's got a time direction and then space directions. And it's really this funny distance with a minus, with minus signs in front of the spatial coordinates and a plus sign in terms of in front of this time coordinate. That is what remains invariant under a Lorentz transformation. So this is a very different kind of geometry, and such space-times, there's a name for them. They're called Minkowski space-time. And it's named after Hermann Minkowski, who was Einstein's teacher, and he's the one who first developed the geometry of such space-time. So Einstein named the space-time in honor of his teacher, who died at quite a young age. So next we are going to discuss the causal structure of Minkowski space. So let's ask the following question. Suppose that we have 2 points, the interval between 2 points, say x1 and x2. So we have 2 points. And we compute the interval. And of course, if I change to a different inertial frame, this interval is going to remain invariant. But now what we can ask is that, is there a reference frame, say S prime, in which these 2 points, x1 and x2, they occur at the same time. So x1 is has time t1, and then its spatial coordinates are, say, let me just denote that by the vector notation of x1, and x2 is t2, the 3 vector x2. And then, of course, delta, then, we can calculate S12. And now what we want to ask is that, is there a way to find a reference frame S prime such that S prime of 1, 2 squared has the form such that the time part is 0? So that this becomes x 1 prime, sorry, x1 minus x2 prime squared minus y1 prime minus y2 prime squared minus z1 prime minus z2 squared. So because, in this reference frame, the time part is 0, we see that this is just a bunch of, we are just adding a bunch of negative numbers. Therefore, S prime of 1, 2 squared must be negative. So this is the condition that has to be satisfied if there is a transformation such that, the interval S12 is taken to another interval such that the time coordinates are the same. So, but of course, this is invariant, so this is equal to S squared or 1, 2. So the fact that, this is negative is independent of the reference frame. So, okay, let me just, review what we have said. So we start from with two events, and in some reference frame, they have some coordinates, say T1, the time coordinate T1, T2, and X1 and X2, vector X1, X2. So this is in some reference frame S. And then we find another reference frame. The question is, when we do, is there another reference frame such that the new coordinates of these points are such that the time coordinate is the same? So if that is the case, then of course S prime squared of 1, 2 will have minus X 1 prime minus X 2 prime squared. And we found that this will happen if the square of the interval is negative. So any point which whose interval is negative, they're called space-like separated. And points which are space-like separated are such that you can always find a reference frame such that those points are, in some reference frame, they happen at the same time, that they are simultaneous. So similarly, we can ask if there are, two events, say x1 and x1 and x2, is there a reference frame such that they happen at the same spatial points? Their time may be different, but they happen at the same spatial points. In other words, if I start, say, in some reference frame, so we have T1 vector of x1 and T2 vector of x2, then in our initial reference frame, it's we have T1 minus T2 squared minus x1 minus x2 squared. So in our new reference frame, we only want the time part to be non-zero. So if such a transformation exists, say from this thing to x1 mu prime, x2 mu prime, where the time part is, say, t1 prime, and here is t2 prime. And the space part is x1 prime here, and here it's also x1 prime, so that when we take the difference, they cancel out. If that is the case, then these 2 points are known to be time-like separated. So if 2 points are time-like separated, then we can see that this is positive. So, because this is S12 and this is invariant, so the condition that there exists a Lorentz transformation such that two events can be lined up so that they are at the same spatial points is that the time-like, the square of the interval is positive. So points whose interval satisfy this condition are called time-like separated. So if I now take some point in space-time and let's call it O, then all other points in space-time are related to O in three possible ways. All these other points can be separated from O in a space-like fashion. So it's like space-like separated, or they can be time-like separated, or they can be separated in a light-like fashion. So we can express this in a diagram, and the diagram is that we have some, coordinate system like this, so their time is flowing in that direction, and the spatial coordinates are, so this is, say, one of the spatial coordinates, say, x, and there's another spatial coordinate, say, y, going in that direction, and this is the point O. Let's use a different color. And then what we want is that all the points, so if I draw now a cone, which makes an angle 45 degrees with the time axis and 45 with the time axis in the negative t direction, then all points, say, inside the cone, their separation from O will be time-like. And there will be a reference frame in which, we can, this basically, this point will be O, but say this is a P, this is Q, this is R, this is S, this will become P, this will become Q, this will become R, this will become S. In other words, the difference between O and all these points will be only have the time-like coordinates, difference of the time-like coordinates. So these are the time-like separated points, and all the points in the upper cone, all these points are called the future of O. And all the points in the backward cone is called the past of O. And these cones are called the light cones. So this is called the past light cone. And this is known as the future light cone. And all the points outside this light cone, they are neither in the future of O nor in the past of O. All these points can be thought of as being simultaneous with O in some reference frame. So for example, this point and this point, they have the same time coordinate, but they're separated in a space-like fashion. So all of these points, you can call them elsewhere. Now, what's happening is that if a pulse of light emanates from, say, this point O, then it'll, propagate forward in time. And as it propagates forward in time, it's going to sweep out this cone. So all the events which are in the future light cone are the points which you can influence from the point O. Similarly, all the points in the past light cone of O are the points that can influence the event at O. So all the points outside these light cones are causally disconnected from O. You cannot send a signal from O to those points. So this is the causal structure of Minkowski space.